Sample calculation E, we're going to consider the following reaction. Here we have CO gas plus Cl2 gas in an equilibrium reaction where it will form COCl plus Cl. So we introduce 2 moles of the CO or carbon monoxide and 2.5 moles of the Cl2 or chlorine gas. These are put into an evacuated 5-liter container and the reaction is allowed to come to equilibrium. The value for K sub C at this temperature is 1.2 times 10 to the negative fourth. So we want to calculate the equilibrium concentrations and K sub P for this reaction. Our first step here would be to calculate the molar concentrations of the initial molar concentrations of the reactants. So the molarity of the CO or carbon monoxide, we take the number of moles, which was 2.0 moles, and divide it by the volume of the container, 5.0 liters, to get 0.40 moles per liter of carbon monoxide. The molarity of the chlorine is 2.5 moles of chlorine divided by 5-liter volume, which gives us 0.50 moles per liter. We'll then set up an ice chart for the reaction. This is the ice chart for the reaction of CO plus Cl2 yields COCl plus Cl. So our initial concentrations of CO are 0.40 moles per liter. Of the chlorine gas, or Cl2, is 0.50 moles per liter. Our COCl is 0 moles per liter, and our Cl is 0 moles per liter. Our change, because as you look at this, the stoichiometric coefficients for each of the reactants and products is 1, or are 1 for each of those, and that's good news for us because it means that all the changes will either be minus x or plus x. So for the CO, it will be 0.40 minus x, for Cl2, 0.50 minus x, and for the change for COCl and Cl will be plus x respectively for each of those. At equilibrium then, the equilibrium concentration of CO will be 0.40 minus x, for Cl2, 0.50 minus x, and then the concentrations of COCl and Cl will be x for each of those. So once we've gotten the ice chart, we can then write the equilibrium constant expression and solve for x. So we're going to take our values from the ice chart that we've done and put them into the equilibrium constant expression. So our K sub C value is 1.2 times 10 to the negative fourth, and that's going to be equal to the product of our concentrations of our products on top, which is COCl times the concentration of Cl, divided by the product of the concentrations of our reactants, which is concentration of CO times the concentration of Cl2. We substitute in our x values, so we have x times x on top, divided by the quantity 0.40 minus x times the quantity of 0.50 minus x on the bottom, representing the reactants. We can simplify this further by taking our 1.2 times 10 to the negative fourth is equal to x squared on top divided by 0.20 minus 0.90x plus x squared. That's just multiplying through the concentrations of the carbon monoxide and the chlorine, our reactants. Now we're going to go ahead and simplify this a bit further by taking our expression on the bottom of the right hand side of this equation and multiplying both sides of the equation by it so that we can isolate our x squared on the right. And if you'll notice here as well, I'm changing the way the bottom expression is written so that it reflects a more standard quadratic form. So here we have 1.2 times 10 to the negative fourth times the quantity of x squared minus 0.90x plus 0.20 is equal to x squared. And again, this was done just simply to put it into a form so that when we go to use our quadratic equation, we have a, b, and c lined up very nicely. My next step is to combine my x squares and get this equation set up so that it is equal to 0, so that we can use a quadratic equation to solve for x. So I'm first going to multiply through the left side of the equation by 1.2 times 10 to the negative fourth, which gives me 1.2 times 10 to the negative fourth x squared minus 1.08 times 10 to the negative fourth x plus 2.4 times 10 to the negative fifth is equal to x squared. I'm then going to subtract the quantity in the left side of the equation from both sides. So on the left, when I subtract that, we get 0. On the right, we'll get x squared plus 1.08 times 10 to the negative fourth x minus 2.4 times 10 to the negative fifth. Now, the reason that x squared appears to just stay x squared is that when you take x squared minus 1.2 times 10 to the negative fourth, in terms of significant figures, there's no real noticeable difference between them, and it would just round to 1x squared minus 1.2 times 10 to the negative fourth x squared is essentially 1x squared. And again, we don't show the 1 because coefficients of 1 do not have to be shown. But we set this up. 0 is equal to x squared plus 1.08 times 10 to the negative fourth x minus 2.4 times 10 to the negative fifth. Now that I have the equation set up in a form that I can use the quadratic equation to solve for x, I'm going to write out the steps of solving this as a quadratic. But here at Ontario High School, one of the things that I recommend for my students is that they get a program for their TI-83s, which most of our kids use here, that it's essentially called a quadratic formula equation solver program. And there are some of these out on the web. Our kids here at Ontario High School get them from their math teachers that have these. So it will save you a lot of time. And quite frankly, at this level of chemistry, my interest in your problem-solving skills is not whether you can crunch out a quadratic like you're going to see it crunched out here. My interest is that you can identify how to set up the quadratic, and then if you use the graphing calculator program, or you can even go out on the internet, and there are quadratic equation programs that you can access by the internet, where all you have to do is plug in the values of a, b, and c from your expression, and it will generate the two roots that represent x for you. It's a huge time saver, and for us here, we test in 46-minute periods, so I recommend that my students use the program to solve for the quadratic at this point. As long as they know how to set it up and they can identify what A, B, and C is, I consider that adequate for the documentation to show me, and then they can use the program to save time as they go to do this. So anyway, here's the general form of a quadratic equation. X is equal to negative b plus or minus the square root of b squared minus 4ac divided by 2a. And then below that you see the equation with the numbers plugged in. And I'm going to trust you to read these numbers. If you need to pause the podcast and read these through and write them down, you're certainly welcome to do so. But I'm going to go through these next few slides showing you as I simplify and solve this quadratic equation expression. I'm going to go through that fairly quickly in terms of talk. One, because I've talked for a long time on this slide, and I would prefer you, if you need to, just pause the podcast and read, and you'll be able to get everything that you need out of it. On this slide, you can see that I've simplified the 4ac expression inside the radical, and that's essentially all I did on this one as we progress through. Again, please read this carefully. Pause this if necessary for you to follow through, but I'm going to trust you to do that. Come to the end of part 1 4 of the Equilibrium video podcast series here at Ontario High School. Quote from Mark Halperin to close this out. You'll join me sooner than you know in a place with no illusions, where the truth is the only architecture, the only color, the only sound, where that which we sense merely on occasion and which takes us up and gives us the rare and beautiful glimpses of the things we truly love flows in deep rivers and tumbles about like clouds in the sky.